Hello, everyone, and welcome to the AQUALIS Sustainable Water Compliance Summit session. Lo and behold, barometric changes and amplified storm events. My name is Katie Johns, and I'm the editor-in-chief of Stormwater Solutions. Before we get started, I'm going to explain how you can participate in today's event. First of all, if you have any technical difficulties during the event, please put your question in the questions window, and our technical experts will help you out. Additionally, we welcome questions during today's session, and we'll answer as many as we can during the Q&A session that will follow Sunny's presentation. But please feel free to send in your questions at any time. To do so, simply type your question into the Ask a Question window on the side of your screen and hit Submit. Also, please be aware that today's session is being recorded and you will be emailed when the archive is available. At the conclusion of the webinar, you will receive an email with a link to download your certificate, which can be used to submit for credit with Stormwater University or serve as one personal development hour for attending today's webinar. Certificates will be sent to attendees who viewed this session for a minimum of 50 minutes. For those viewing on demand, you will need to complete and pass a short quiz at the end of the session to receive your certificate link. And now let me introduce you to our session speaker. We have Sunny Wescott, Chief Meteorologist, Emergency Response and Operations Support. Chief Meteorologist Sunny Wescott specializes in extreme weather events impacting emergency response, supply chain, and critical infrastructure. During her time in the U.S. Air Force as a national-level lead meteorologist, Ms. Wescott trained on continental and oceanic weather as a top forecaster for her support region and is considered a subject matter expert for multiple climatological events such as drought, subsidence, wildfires, tropical cyclones, and winter storms. Sunny has also graduated top of her class for her degrees in Homeland Security Management, Public Safety Administration, and Atmospheric Sciences, building on her skills as an operational forecaster. She now provides national and international extreme weather-focused impact reports for supply chain, critical sales, security, and key interdependencies such as energy, water, and telecommunications before, during, and after disasters. So with that, the floor is all yours, Sunny.
Okay, hello everybody. So I'm going to be talking about variations in weather that are occurring from the top of the atmosphere down to the surface. So it's not just going to be your standard, this is the forecast, or this is what's happening and why it's happening. It's a lot more of drilling down through the atmosphere, what's occurring, why it's occurring, where it's occurring, and some of the trigger points for what we're going to be experiencing going forward. So as you can see here, one of the things that we're going to be talking about is when we're looking at model data and we're looking at the temperature margins over the years, what that means when it comes to all of our model forecast, all of our engagement opportunities, when we're talking about critical infrastructure, putting in new materials, doing outreach with emergency managers, doing outreach with different suppliers. When we're looking at the supply chain globally, this is something to keep in mind is where we're looking at the 10 hottest years on record, which you'll notice all of those colors represent most recently. All 10 of those hottest years on record have occurred since 2015, which means our past decade has been our hottest decade in operations. Now, what that means is that for all of our built infrastructure, for how you operated, where you built, what you built, this applies to everything. So when we're looking at the black line at the top, that was actually last year's temperature. So you can see why some of our models may not be forecasting the intensity of the storms correctly, but will be highlighting the period of time and the area to be impacted. It's just the intensities are starting to grow outside of what the models are capable of forecasting, because as you can see, we're in record break as a perpetual. So what we're going to be talking about moving forward is really what happens when there's an uneven distribution of heat. Now, what that means is that the heat really is changing, not just in one state or one region, but in the global capacity. Some of these countries are warming while some of them are cold, sure. So if you had an abnormally cold winter, there's a chance another area saw an abnormally warm winter, which changes our pattern. So if you think of all of our frontal boundaries, all of our low pressures, they're what produce our rain, our snow, our winds, our thunderstorms, even our tropical cyclones are lows. When you're looking at this as an upper atmospheric, you're looking for lows and highs. They usually follow one right after the other. So it goes low, high, low, high, low, high. Moving across the entirety of the belt for the Northern Hemisphere. For us here in the US, that's the polar front jet most predominantly. What we're looking at is a major trend of change. is a twofold. When you have abnormal heating, the atmosphere that we know, our troposphere, where all of our weather occurs, our clouds are, where we operate down at the surface, all the way up to the top where those anvil clouds that make the thunderstorms usually flatten out. When it gets abnormally warm persistingly, as it has been, our top of our troposphere, our tropopause, actually lifts up a little bit. Now, what that ends up doing is it creates more space for these lows to be deeper and the highs to be higher. Now, what does that mean when we're talking about operating? It means that the lows are taking on different intensities and the highs are taking on different intensities, and they're following one right after the other. So that's causing a merry-go-round of unpleasant weather for the rest of us down here at the surface. When a storm enters the US, it continues on a track path from one side of the US to the other, usually entering from the west, either from California up to Washington or from the northern plains, the Montana to Dakotas area, drops down along the Front Range or the central plains of the US, and then exits out to the Atlantic, moving a little bit further to the east, pushing over into Europe, pushing across Russia, China, entering back out into the Pacific, coming back across to the US once again. So think of it like a merry-go-round, with the horses on the merry-go-round being your lows and the area between those horses being your highs. Now, what does that look like when we're talking about weather events? If we're saying that your lows are getting deeper, that means they're getting stronger, more winds mixing down, more persisting winds. You may have noticed that your thunderstorms are producing stronger winds. You may have noticed that your windy days are windier than usual. You're seeing more tree damage. You're seeing more evaporative demand, more vegetation strain because of that. You're also seeing that the lows are producing more hail, more lightning strikes, more tornadoes per tornado day, heavier rainfall in shorter periods of time, heavier snowfall in shorter periods of time. All of this is affiliated with the slowing and the deepening of the low pressures. Now, when you have slowing and deepening of lows, you have high pressures, the area in between those picnic days, the clear sunny days where you want to go outside, but also your heat domes, your cold air damming, your stagnant air advisories, your high direct solar radiation days with high UV and evaporative demand. That's the in-between of these low pressures. So when you're seeing a change in one, you are seeing a change in the other, and it's never just one country that's playing. Anytime here in the US that we're under a heat dome or we're under a flash flood event with severe weather, somewhere else in the northern hemisphere is under the exact same weather event, which is going to strain the global supply chain for restoration on the back end of a lot of this. So what we're looking at when we're talking about how do I forecast this, how do I visualize what Sunny's talking about, you can actually pull up a ton of free tools that are out there for everybody in the general public to understand what it means to see a storm system like this come into the US. So as you can track here, our low pressures, those L's on the screen, anytime that they start to get that purple wraparound, that's called becoming a, going from a mature to an occluded system. So it is now a ultimate like low pressure. It doesn't get much stronger than an occluded system in the sense of it's got a full wraparound. It looks like a comma, which is why we call them comma clouds. You'll notice them usually having a strong surge of wind on the back end, severe weather breaking out on the front end, and then heavy dumping of precipitation along the warm front. And then they're usually a bit slower moving once they take on those purple pips, the occluded front. So you can see these in the upper levels at the 500 to 700 millibar. You can see them down in the surface and the turning in the winds. And then in some cases, because these winds are getting so much stronger, you're seeing a coupling of another weather event, our dust storms. And our dust storms are no longer just a couple of counties. They're not even just one state. These dust storms are now 3 to 4 states in intensity, covering those areas for hours on end, which is why you're starting to see the news pick up on the word haboob, which is the term that we use in the Middle East when we're talking for deployed people about weather. We're talking about those big dust storms that overtake the city for hours on end, blacking out things with the sand ripping paint off, sedimentation depositing in the rivers and the reservoirs, in pools, the higher levels of different things like fungal outbreaks that can happen and be moved during these dust storms. So across the board, any change in our low pressures creates a cascade of impacts across the US, because these storm systems, as you can see here, that beautiful moisture of the green and the blue and then the freezing in between it, that impacted every state that it crossed, which is covering the entirety of the eastern US from the Great Lakes back through Texas. And then as it moves over towards the east, towards the Atlantic, it'll cover all of the states across the East Coast as well. So this is no longer just a handful of states, just a handful of regions. It is entire swaths of the US that are under these weather events as we go forward. And what this means when we're talking about the changes in the upper levels of the atmosphere, as the atmosphere continues to abnormally warm and expand, it means that these lows will continue to get deeper outside of what we know. That means scientifically, we don't have data to say this is what weather events look like when a low is a certain amount deep or when a high is a certain amount at height. We know that they're incredibly damaging. We know that our infrastructure was not built for it, that because we haven't seen it before, we would not have prepared for it. It would not be in emergency plans. It would not be in material selection guides. It would not have been in our testing for stress tests for a lot of our infrastructure across the board, whether it's concrete, cement, whether it's certain metal grading systems, whether it's different filtration systems, especially for the water sector when we're talking stormwater runoff. So when we're looking at these events taking on greater intensities, because of the uneven distribution of heat, we are going to see these impacts come in uneven waves as the intensities continue, again, on a global scale, which means that at any point, if you need to shore up resources, you will be competing with others. Now, when we're looking at this as a visual and people say, well, are you really sure? I understand you have a lot of scientific studies that back this, but I would like empirical evidence for my particular site. Let's say you live in Illinois, or you live in Kansas, or you live in Florida, and you would like to know specifically by how much it's getting worse for your area. 100% possible to do utilizing the automated sensors. Now, a lot of these sensors were put in just after World War II or just around the World War II era. So these sensors have been around for a long time. We have them all the way from Guam. We have them in American Samoa. We have them over here in the US. We have them in Alaska. We've got them over in Puerto Rico. These have already been here. Every airport's got an automated sensor is a really good example of it. Every military base has these. A lot of buildings have them. You usually see them as the ice cream scoops that are sitting up there spinning in the wind. Those are automated sensors, and what they're doing is they're taking in weather data every hour, and then during major storm events every 2 to 3 minutes, creating averages and storing them in a mass repository of data that goes back decades. So when we're looking at about 100 years worth of data as we go forward, we're continuing to add in new data on top of the old data and needing to reference it utilizing things like AI. You can go back and say, hey, I would like to know, automated sensor, our altimeter and our sea level pressure, have we seen an increase outside of the baseline over the past 90, 80 years of data? It will go back and it will find your averages and then show you where you've hit extremes. Then what you can do is you can go to each day that you can see an extreme peak in one direction or another, and you can find the news stories. Now, we're working on this as an open and free tool for everybody so that you can do this quickly, effectively, and only off empirical data. So you'll never have to wonder where it's getting this information or if that information is valid, because sensors are just that. They are just mechanical sensors checking the atmosphere continuously for a specific site. Interconnecting all of this data makes it a lot more personable for each one of you and for your forecasts. Being able to look at storm flows, you can ask how many times you've seen 5 to 6 inches of rain, and then you'll see a percentage of increase. How many more times is this happening since before? Is the intensity going up, and if so, by how much? So all of these are just different ways that we can look at the information going forward in these beautiful sort of graphics of if we change one thing, what all else changes. So if you see heavier rainfall rates and stronger winds, you know you're going to get more sedimentation depositing into the river, filling the river from the bottom up, reducing the capacity of the river system, reducing the capacity of your reservoirs. And then you'll see these extreme heat events that are jeopardizing the material of the rivers, the reservoirs, the canals. You'll also notice that earthen dams and other clay bases that we have built a lot of our infrastructure on or utilizing will start to bake in the extreme heat and compress in on itself, cracking, which allows for seepage, which allows for wear and tear, erosion, and then subsequently failure. So the earthen dams as a natural system, as well as our built infrastructure with the concrete cement mixtures, are both at jeopardy when we're going forward in either direction of deeper lows or higher highs, which is why it's so important to understand the pivots between the highs and the lows that are occurring and what we're expecting for patterns across the board. Atmospheric rivers, monsoonal flows, tropical season in full with hurricanes. Each one of these plays a role when we're talking about upper level atmospherics. So what does this look like when we're talking about, well, my operations, well, my site, my grid, my state? A lot of this is, well, you built all of your stuff probably somewhere in this window of time. Your metropolitan area in full was developed somewhere in here. Most of your newer buildings, your infrastructure interconnectivity for your water, wastewater treatment plants, likely in here as well. This is everything from World War I, World War II to now. It goes all the way back to a lot of these areas being developed in full. What you're able to see when we're talking about the change in temperatures, it does not need to be a lot to create a pivot in how we experience our weather system. Per degree of warming, so 1 degree Celsius or 1.8 degrees Fahrenheit, the atmosphere can hold 7% more water vapor. Now, water vapor is naturally a greenhouse gas. The more water vapor that we have, the warmer it will get. So the problem is that enough water is continuously evaporating out, moving up into the upper levels of the atmosphere, the intermixing of the lows and the highs, amplifying the capability of a lot of this moisture to stick around for longer. We're seeing more cloud coverage in certain areas, like on the back end of thunderstorms, that are trapping in the heat a little bit more. So you're going to see that this is an inevitability going forward. We're not looking at having the conversation of what if we're able to stop all of it right now and reverse it. That's not going to be the solution when we're talking about how do we build into these weather events. So we have this change in the upper level atmospheric, how much water vapor there is, which then yields a significant increase in precipitation. So that's a 5 to 10% increase in extreme precipitation events at the surface that we are going to continue to see at an increasing rate going forward. So this means that the hotter that it gets, the infrastructure is stressed, and then the precipitation will add in the force and additional stressors. So what does this look like as far as the ins and outs, the day in and day out for each one of our different regions? Well, when you look at February, and March is just released not too long ago, you're able to see these beautiful graphics from NOAA's NCEI team. And what it does is it really cleans out all of the rest of the weather you may not care about. These are all anomalous weather events. These are major events that have kicked off either outside of their seasonal norm in areas that don't typically experience them, or were stronger than usual. So this really cleans out a lot of the noise, gives you something to focus in on, and then you're able to see, okay, across the US, we had a problem in every aspect of weather. We had fire concerns, we had drought concerns, flooding, snow, tornadoes, you name it, it happened in February, it happened in March. We also saw in March record breaks in tropical cyclone activity in the southern hemisphere. We're looking at some of these things in the global side of the house, as every continent, you'll notice in that graphic, is reporting a surge in temperature. So that creates a baseline issue of, even if one state or one region in the US says they're abnormally cold, another state like Arizona or California may say, I've already hit my triple digit days. We're already starting to see 105 plus degrees. And then what we had happen in February, which was a really good example of why this is a problem. In Nebraska, we had 105 degree temperature spread between the lowest low temperature and the highest high temperature in one state in 1 month. 105 degree variance is very stressing for materials, for wildlife, for our various ecology aspects, our river systems, our vegetation, all of the evaporative trends, the capabilities to be able to build anything into that become very strained. So when we're looking at drought, we are looking at these becoming flash events, flash drought, flash flood. These are going to become far more extreme in the onset and the damage that they're capable of producing. What did this look like last year? Well, as you can see, when we're talking abnormal temperatures, a lot of people just assume it's the western half of the US, but actually it's the vast majority of the US that's seeing bleeds into higher temperatures as a persisting average, or an average that's starting to violate their trend and become a record break, either in intensity or longevity for the month. So you'll notice that the year to date from January to December for last year, most of the US had these increased temperatures, which yielded an extra 657 tornadoes against the average. Our average annually for the entire US is about 1,200 throughout the year. We saw a significant increase in spring tornadoes last year that yielded hundreds of excess in areas that don't typically get them. We had tornadoes in Alaska, we had tornadoes in San Francisco in December. We're starting to really see these not only impair operations, but really our transportation network in full, which is our supply chain. So when we're looking at damages, we're looking at costs across the board for all of these different sites, and we're looking at this not going away anytime soon. So as you'll notice with the graphics from the National Climate Assessment that most recently dropped just a couple of months ago, you'll see that the temperature increases in every season are going to become more problematic. That means more snowpack melt. It means more snow at once also. This does not mean that you won't see your winter. It just means that your entire winter is no longer going to be many months of winter. It's going to be a few months, and then it'll be a few events. It's going to continue to shorten into extremes, giving you all of the precipitation that you want, and even maybe more, but in a handful of events, which your vegetation's not used to, your soil isn't capable of handling, your trees can only block so much of that force-wise, and then, of course, all the rest of that overwhelms our stormwater systems. So this is across the board an issue. This isn't just our continent. This is happening in every country. River systems are overflowing right now in Russia. We're having major storm events outbreak in China, across Europe. We've seen flooding, drought, fires over there. We've seen Australia get hit with numerous tropical cyclones. They jumped from a non-existent tropical low all the way up to a category 5 right before landfall in less than 24 hours, and that was just a couple weeks ago. So that definitely makes us concerned for what we're expecting to see this year, but also as trends going forward. So looking at some of the changes in extreme weather, our severe weather side of the house, unfortunately, when it gets so hot and so humid, those two go together quite well. It creates a sauna-like effect in the US, which, as you know, you can make it incredibly hot and humid in a sauna, but you can't make it rain. You need that low pressure. So the hotter and more humid it becomes before the low comes in, the more energy you're providing for the storm, which is allowing for our storms to not only get taller because the atmosphere is getting taller essentially, but to produce more damaging events. So more lightning strikes. We're expecting for our supercells to stay on ground longer, to cover wider areas and become more destructive in nature. So they're not moving from Tornado Alley outward. They're expanding from Tornado Alley to Dixie Alley, and then everything in between is going to see an increase. So Tornado Alley being that central part of the US, Dixie Alley being all of our Gulf states. So if you can imagine expanding to cover that, you're going to see an increase into the Great Lakes areas. And that's going to be something where we see the lightning strikes go up. Australia reported 2 million lightning strikes in a single storm event earlier this year. Definitely on docket this year for lightning damages. So if you have external infrastructure or you're reliant on the grid for something, this is going to be a concern. If your substation gets struck by lightning, catches fire, and then you're not able to operate your pump stations, or you can't operate your release, you can't operate pretty much anything without your energy sector. If it takes damage to the transformer like that, Heathrow Airport just in the UK a couple of months ago is a great example of that. When something happens to the energy sector, it impacts all the other sectors. When the supply chain is delayed or degraded because of these weather events taking on greater intensities, everyone's involved in that. So this is something that applies across the board, regardless of the industry, regardless of the critical infrastructure sector type. When we're looking at who's playing which games in the US when it comes to heavier rainfall events, not everyone's playing the same way. Some areas are going to see heavier rainfall earlier on. They're going to see it more persisting than other areas are. Now, you may look at this graphic and you say, well, Sunny, why is the central US not as intensive when we're looking at flash flood events? That's really not what this graphic says in the bottom sort of strain of things. You'll notice that the front range of the Rocky Mountains is what it's depicting there, which is where we typically have our dry line. And that dry line exists as a feature off of the Rockies into the plains. And what it does is it creates a conveyor belt of thunderstorm activity. It's a natural developed area of severe weather. So when we're looking at flash flood changes, that area already sees flash flooding. So it doesn't necessarily see a major increase in those events because it's the start of the conveyor belt, if that makes sense for everybody. So when we're looking at damages, we're really looking at them to start to go up across the nation. We're going to see these 1 in 1,000-year flood events occurring a lot more often for certain areas that we're expecting to see an increase in the 1 in 100 and 1 in 500. So just taking that notion out of mind and saying, am I prepared for a record-breaking flood event for my area? How much is too much to continue to operate? And when will that be in the forecast? So when we're looking at increases in those flash flood events, this graphic is very helpful to understand what's changing. This is not your flash flood graphic. This is from NASA, a change in the water cycle graphic. So what this means is that you're getting all of that rain, all of that snow coming down at once, but it's also going through the entire water cycle quicker. It's evaporating back out faster. It's melting quicker. So this is more important to focus on for a lot of the US And then in other areas where they've done their water management planning based off of tropical cyclone frequency, tropical cyclone continuation in smaller amounts of precip, not heavier dumpings of it, atmospheric river sizes, entry frequency as well on the other side. So the areas that are facing those red colors, as well as some of our areas in the monsoonal path for like Arizona, that's where we're seeing changes in the trends that they had built into a more comfortable side of these weather events. And if the weather events take on greater extremes or they slow down in frequency and they become more heavy hitting, then it creates a larger issue for their averages. And that's really what we're talking about when we're looking at this graphic. So some of the ways that this is important to consider for stormwater or for any of the water sector in full is that we are expecting for our cities to see as much as 30% more annual rainfall than today, and 1.5 times as many days with over an inch of rain, which is correlated with the graphic on the last slide as well. So this is being understood across the board. Again, not just here in the US, this is already occurring on a global platform for multiple different countries, both northern and southern hemisphere. We just have opposing seasons. So when we're looking at this, we are looking abroad and we're looking at how much rain are they seeing, which means the atmosphere is capable of producing that much rain. So it's important to look at other countries. How much are they seeing? What kind of damage did they see from it? How long did it take them to restore? What was the general consensus from the public on what it meant to operate in that? Because when we're going forward into this coming winter, if we're going to be entering into La Nina right during the peak of hurricane season or even touching upon it, then we're looking at greater swings in temperature going forward for this winter and subsequently further on down the road. Whether you like federal data, you like individual scientists, you like nonprofits, there's data of all types in the slide deck, and you're going to get access to all of these PDF slides and all of the different links for the studies, the graphics, all of that made available to you. So you can see in this one, this is from Climate Central. They're a fantastic nonprofit. I recommend playing around with some of their graphics as well as First Street Foundation Risk Factor. When we're looking at some of these, you can personalize them by state, by city. You can look at the overall US trends. You can watch videos where they explain it. They have great statistics, but you can see that when we're talking about the warming events, we're not always talking about the same region. It depends on what weather type we're talking about, what season we're talking about, and what sort of pattern abnormal shift that we're expecting. So with here, you'll notice that most areas are starting to see an increase in their warming days, which explains why our snowpack is not sticking around as long. But it also highlights other concerns for what we're going to be seeing in the other seasons. So if we see that warming in winter, we're going to see changes in our spring. So this means that the opposite side is going to see a major pivot in the spring temperatures, which we're already seeing right now. We're seeing over 105 degrees in a few states. And we're expecting for that to continue to surge up, looking for, if you pay attention more to the Farmer's Almanac than NOAA, they're also calling for a record-breaking summer this year. So this is across the board. Everybody is in agreement that we are warming. It is warming even by a fraction of amount, which is causing a trigger to all the rest of our weather events. It's causing more pollen to be growing in separate waves. So expecting dual waves of pollen, which is awful for me with my allergies. We're also expecting the growing season to have dual pivots. If flowers come out, if our plants, if our vegetation, if all of the different things that we rely on for the ecology and the stability of it start coming out prematurely and we get a late season freeze, that's going to damage the crops. But if we also see them come out too early and we don't have water allocated for them, that drought will also damage them. Plants retain the stresses and strains that they've gone through and they pass it on to their seedlings, which can then create a cascading impact to how we operate, who we distribute to, how much we're able to move, where we're even getting the water from, and where our farmers are going to be growing as we go forward. So again, if we're looking at changes in all of these things, we're looking at the episodal, the longer term shifts in our precipitation. So to say that if we're warming by a certain amount now, and we're expecting for that to continue for decades, then we're definitely concerned about what that means for the continuation of our snowpack. Our snowpack operating as a longer term storage system, a reservoir that slowly bleeds into our river system, which we use to allocate the dispersal of who gets what amount of water for what purposes. This is going to become a major issue as we go forward because we're not expecting as much snow. We are expecting precipitation, 100%. It'll shift from snow to freezing rain, then from freezing rain straight into rain, and then we're going to have far more rain than we're used to having during these winter months. Now, that's going to be a problem for icing. It's going to be a problem for icing to develop inside the soil systems, further damaging the roots because now the ground will freeze, thaw, which will kill off plants and damage concrete cement mixtures. So when we're looking at this, we're looking holistically at the problem. If this does occur, are we prepared for what that damage may bring? And when we look abroad, we can say that no other country really has the solution in hand, or they wouldn't be seeing the same damage points we are. So when we're looking at this, as far as where we're at right now, you'll notice that the April snowpack was already accounted for, and some states were better off than other states. But overall, over the last 3 weeks, we have seen a major drop off in snowpack because of the evaporative demand. A lot of the states started warming up too quickly. We also saw an increase in the amount of runoff not making it into the river system. Now, this creates an additional issue because that means that our soils and our vegetation are drier, and that means that they're pulling in more moisture. Less is going to be available. That's going to end up pitting states against each other as far as allocation rights go on shared agreements, both for river systems, surface water, and for aquifer systems, groundwater. All of these basins are shared water repositories. And when we're saying there's a change in the pattern of water, this means there needs to be a change in the pattern of operations to match. And because this is all record breaking, this means that we have not trial and errored what it means to see a pivot like this last either indefinitely or even just for decades on end. What do we do when we run out at different points of the river system or different points of the aquifer system? And how does that impact operations for things like planning our snowpack? So when we're looking at the uneven spring warmth and winter warmth, and what does it mean for the snowpack? And we're talking about, well, there's eventually going to be more rain, there's going to be more ice. It also means the snow that we do see is destabilized. It's too much snow at once. The ground isn't fully frozen, or if it is frozen, maybe it has an ice layer that's already formed. The snow pours on top of that. We're seeing an increase in snow algae, which is darkening our snowpack a little bit too much, which is allowing for it to overheat. Now, this is also an issue during wildfire season when we start to see some of the aerosols from the wildfire smoke deposit onto the snow, darkening the albedo. What's the difference between a white car and a black car in summer parked in the same parking lot? The darker car is going to get hotter. It traps in heat. So if we're saying that our snowpack is getting darker, this is a major concern for how we're going to operate going forward. It also means higher levels of arsenic and mercury in the water system because those elevate and lift up. During wildfires, they become aerosolized and they deposit and then subsequently feed the algae blooms, both in the snow and in the river system. So there is going to be a continuous increase in that problem set as we go forward, as well as the threat of destabilized snowpacks coming down in force, doing damage as they move. Now, when we're looking at where are we at right now? Just a couple of weeks ago, this was our drought view, as well as all of our reservoirs. Again, some areas way better than other areas, but not all of them interconnected. So this is going to create an issue on the have and have-nots when we talk about water security. But also when we talk about water that is lower level for too long, gets too warm, that creates an issue when we're talking about bacteria movements as well as fish shifts. So when we're looking at these different fish moving into the areas, some of these fish becoming more aggressive, they're becoming larger. There's changes that are happening across the board when things pivot by a small amount. Aggression rates are going up in some of our marine life, so we're seeing more shark attacks, more alligator attacks, which of course creates an additional issue at the mouth of the river systems in places like the Gulf or along our coastlines. So when we're looking at movement of water, and we're looking at movement of wind, and we're looking at drought, and we're looking at direct sunlight, and we're saying that there's going to be this major shift because the lows and the highs are pivoting, this is what it looks like at the surface when we're talking about the threat going forward, is year over year seeing states in drought that were in drought for the last 5 to 10 years, maybe even back as far as 20 years. Their vegetation is starting to see a pivotal shift in where it's able to form, how it's forming, and how flammable it is as we go into the fire year. So when we're looking at the evaporative demand of the atmosphere, how thirsty the atmosphere becomes, NOAA's also got a great graphic for this. It's called the EDDI, the Evaporative Drought Demand Index. Visually, it gives you a really good indicator on where your wildfire threats are likely going to be over the rest of the year. So if we're looking at drought rates going up, and we're looking at the root zone soil moisture indicator from NASA's GRACE satellite, and we're looking at where the root of the trees may not be touching water anymore. So when you go out to dig a well and you say, well, I had to dig that well down hundreds of feet, that tree that's nearby is tapping into the same groundwater, is unable to dig down that deep on nature. So thereby, it will likely die off, take a couple of years, which is why we're seeing so many more trees go down now than we had historically. We're also seeing that this puts us at greater risks in different pockets than we're used to planning for wildfire activity. So you'll notice, again, it's not the West Coast that we're paying attention to for wildfire season right now. Even though they've already burned so far this year, We're really worried about things like the Appalachian Mountains through the southeast. We're worried about the Central Plains up through the Great Lakes. We're worried for Montana. So when we're looking at these maps and we're looking at the indicators, that we're understanding the overall pattern shift for what it means for the year, not just what this week's forecast is, but what does it mean to have seen a pattern shift at this rate going forward. So when we're looking at the runoff rates, if you lose your trees, if they die off because of a fire, you don't have the same force blocking. You don't have the same shade. You don't have the same force blocking for the water when it does come in. So now more of your soil is getting stripped away. There's more friction, more force. There's also hydrophobic layers forming from the heat from the fire and the heat from the direct sunlight. So when we're looking at this as an overall impact, what does it mean to lose the water in the soil? One, you have subsidence issues. So your ground's starting to compress and collapse, rip open, fissures opening up in Arizona, Utah, New Mexico. That's a major issue. When we're also looking at these earthquakes that we're starting to see kick off, you'll notice a lot of these earthquakes are happening in areas as they're reaching peak drought right before either a flood event or right after a flood event. When there's a major compression of force on the soil that was weakened over time because there was no moisture in it and it crumbled. Now, when we're looking at earthquake activity, the more moist soil is, that changes how our earthquakes trigger. It changes how much damage carries through the soil, how far out that shift occurs. All of this makes sense once you start to really put pieces together. You already know a lot of this. You've just never thought of it in implication of a larger thing like either seismic systems, operations, the tectonic plates in full. But we know that water weighs a lot, and we know it falls to the lowest elevation, and our lowest elevation is often our fault lines. So we know that our water system is crucial to keeping our tectonic plates stable. Now, when we're looking at wildfire threats going forward, and we're talking about, well, we're going to see this impact with our vegetation no longer shading the soils becoming unstable, the plants are dying off too fast, there's too much direct sunlight, there's too much wind. What does this look like for fire threats? Well, we're definitely looking at Hawaii going into the summer. We're looking at parts of Alaska right now through the spring. We're looking at each different state carrying a different threat matrix for it. So this isn't to say, oh, we're expecting the Southwest, the Central Plains to be the fire concern. New Jersey, the last couple of years, has reached record wildfire sizes in their national forest system. Florida's caught fire multiple times. The marshes have caught fire in some states. If we're seeing this starting to burn different vegetation types, this means that a lot of these different areas are at risk regardless of their historics. So we're looking at what is the situation currently, not what has the situation been historically. So again, just using historics as a foothold of what kind of damage could we expect from this kind of weather event. So when we're looking at wildfire threats for this year already, we're in the top 3. So we're in the top 3 for most active years in the past decade already. And this is putting us against those record-breaking years like 2022. So when we're looking at 2017, 2024, 2022, as our comparables, and those years were devastating for the US, we're definitely looking at major concerns going forward for too much harmful material making it into our water sector, losing the critical vegetation. And what do we usually plant right after a major fire? We do not plant another major tree. We usually plant a seedling. That seedling is now expected to be able to live through an event that killed off a mature tree. So when we're looking at this as an overall ecology shift, looking at where the pyrocumulus clouds are depositing the arsenic and mercury, we're looking at where that runoff is feeding the algae blooms, what the algae blooms are doing to the fish, to the people, to the wildlife. When we're looking at the algae blooms clogging up water intakes, we're looking at harmful algae blooms going forward. What does it mean when they dry out and aerosolize and carry on the wind and you inhale them? Same thing with valley fever. What happens when a fungus that grows in the monsoon spreads over the sand, dries out, aerosolizes, and you inhale it? You end up with spores on your lungs, and this creates a larger issue, making you more susceptible to dying from various other illnesses. So it's not just bacteria in the water, it's fungus, it's the algae, it's all of these other problems that are being amplified at the same time because there's a major ecology shift, because the upper atmosphere is changing. So it isn't there's 20,000 problems at the surface, it's back it up. There are 8 main weather hazards being amplified, back it up. There are 2 main pivots occurring because of one thing, which is the atmosphere is shifting. So when we're looking at how that operates going forward, we're looking at changes in everything. Changes in how our river systems get to the water, the ocean, the main body water systems, or the Gulf. We're looking at heavier rainfall rates, changing the charting paths, changing our washes. We're also looking at, when you think about how water gets into the groundwater, all those recharging points where water feeds in, it's coming in too quickly. And what that's doing is it's changing some of the aquifer entry paths as well, bypassing smaller aquifers, which is why we're seeing aquifer collapse in some areas, regardless of the amount of water coming in. It's not draining in the same way. So this is a major pivotal shift in thinking and operating that has to occur based off of the science in the areas, using things like INSAR mapping. So when we're looking at different river systems, we're looking at major events like the hurricanes coming in. The amount of water that dumps down charts new paths going forward, needs to be mapped and planned for. You can't just undo what's getting done at this point. You have to build into it. So that's a big part of when we're talking about how do I map this? Where do I go? Where do I find this information? There's tons of new sites that are popping up every couple of months from different scientific communities. Again, whether it's NOAA, whether it's an international group, whether it's just a data scientist who's mapped a bunch of things together. All of these are available to you. You just have to know either who to ask or what to ask. And a big part of that just comes down to understanding the full cycle of threats as they're developing. So the subsidence issue is going to continue to get worse. It's going to damage far more infrastructure than you're ready for. And it takes years for it to recharge, if it recharges at all. So if you lose your groundwater, if it dries up because there's a drought, you overpump it, or the surface water dries out or changes, then what you're looking at is a soil shift for that entire area to start compressing down. If it compresses fully, you lose that aquifer permanently. What does that mean? Looking at Utah is a really good example. Once the water does try to recharge into it and it's compressed in, it doesn't have anywhere to sit anymore, so it'll start to bleed back up, which is why some basements flood from underneath, even though there's no surface water on top. So again, when we're looking at some of the different threats, this is absolutely one. It's going to damage a lot of different infrastructure that can't handle being tipped or compressed in different directions that are uneven, which includes our cityscapes. So when we're looking at the atmospheric rivers, obviously they're playing the same game that the tropical cyclones are playing, that the continental systems are playing. They're getting larger, more heavy hitting, but they're slowing down. They're not as frequent. This creates a bigger issue with planning when you're trying to advocate preparedness and it doesn't occur for a full year and everyone forgets about it. And then one event kicks off that's devastating. So to be aware that when you are seeing these events, they are hitting harder, and they're hitting harder for everyone. Atmospheric rivers are not new. They've been around since we've had weather events. So to be tracking China seeing the same thing, our monsoon getting worse, India seeing the same thing, our heat waves getting worse, India seeing the same thing, our river systems overflowing, Russia seeing the same thing. You can see these in every other country as they're hitting and what they're doing and why they're doing it. We are expecting our waves to get taller. Winds are stronger, lows are deeper. Waves will get taller. So moving off into the ocean is not the solution. Needing to make sure that you're shoring up your coastline, that you're planning for the waves to push into your river systems, to push into your water treatment plants, your canals, to bleed the salt water further in, to eat away at the coastline. All of these things are occurring. The tide is going up because there's only so much water on the earth, and once it heats, it expands both into the air and at the surface. You know this, if you boil a pot of water on the stove, it'll expand. Some will evaporate, but some will boil over. Same thing with our surface. So to be aware that this is empirical evidence, this is happening everywhere. We're able to see this in different coastlines that were settled at different decades, different centuries. We have centuries of sea line, to just keep that in mind when we're talking about modeling. Tropical cyclones getting worse. We're running out of time, so I'm going to speed up just a little bit to get through these last couple of slides here. Tropical cyclones expecting to intensify a lot more. Looking at category 6s is not going to happen because technically anything over a category 5 is as devastating as a cat 5 is in concept, catastrophic damage. So when we're talking about category 6 in notion, we're just saying that there's going to be record-breaking winds and that we understand that Milton was the strongest tropical cyclone on the globe last year and it came out of our Gulf. So warm water plays a huge role in that, as does warm air. We're expecting more EF3, 4, and 5 tornadoes with our tropical cyclones. So if it's not enough to get hit by one, you'll get hit by all of it. So again, we're looking at each one of these taking on greater intensities. We're expecting more landfalls because the lows that move across the coastline are usually what fight off our tropical systems. So usually I have this beautiful phrase, you can feel free to steal it. Hurricanes can't jump fronts. If you have a frontal boundary, it's an ultimate weather feature. That's where you see the hurricane approach the coastline and boomerang away. That frontal boundary acts as a wall. So if I'm saying that your fronts are slowing down, that means there's a bigger window of opportunity for a tropical cyclone to make its way up and in, because a tropical cyclone forms from the surface to the mid-latitude, mid-elevation, altitude. That was the word I was looking for. And so when you have these smaller storm systems, that's how they're undercutting and moving into the U.S., why they're so damaging. Hurricane Helene was a tropical cyclone that merged with a frontal boundary over one area, so that amplified both. Very similar to what happened with Hurricane Sandy, with Hurricane Harvey. When you look at the continental systems, you get a way better understanding of what you're expecting to see from all weather events. So having a better understanding puts you in place to understand that Colorado State University has put out their forecast, as has many other, that we are expecting to see a more active season in intensities as far as major hurricanes go, as far as landfalls go, and especially watching the Gulf because it is abnormally warm. It's a smaller body of water, easier to heat. It's also got a loop current from the Caribbean. So as the Caribbean warms, so does it. Subsequently, more problem sets for things like red tide, as well as the sargassum coming in and the problems those bring as they die off on the coastline. So we're looking at all of our built infrastructure along the coast for threats from sea level rise, from threats from tropical cyclones, all of these additional problem sets to say that when we built for the area, we built for the climatological norm. We did not build for the extreme that we're seeing now or the pivots that we're seeing now on average. Now, when we're talking about average pivots, we're looking at things like the moon wobble. So if you've ever heard me speak before, this is one of my favorite things to bring to everyone's attention. This kicks off in the 2030s. If you have flooded out any time in the past decade, to be aware that you are in far worse conditions in the 2030s for continuous flooding concerns. It's just the way in which the droplet of water that we rotate within wants to be with the moon because of how the moon interacts with it. So the moon will tip away from us in the 2030s as it rotates, which will cause the water to form a teardrop shape as we rotate in it, causing us to rotate into the highest high tides we have seen so far. So again, just other things to be aware of on this, yes, wonderful, happy Earth Day for everybody. Other things to be aware of, our grid's not ready for what's happening. As we've built up the grid, as we've improved our grid system, you'll notice we're still seeing power outages go up. Regardless of how much we're able to do right now, the weather events are still beating us. Severe weather is the #1 cause of power outages. So if we're saying it's going up, it's going to get worse. Power outages will go up as well. So these are just fantastic graphics to be aware that severe weather leads the way even outside of tropical cyclones, because severe weather is all year round and across the US. So again, just looking at some of the different ways that we can mitigate this is how we're going to end the conversation. Flood barrier systems are fantastic, but you need to deploy them in a community review. You can't just do one site, because when you change the flow of water at one spot, it'll flood out the community downstream from you, and then you could be sued for that. So just to be aware that too much water is bad for everybody. I know everyone needs water in different ways. You need to find a way to make the most use of the water that you are getting and to be able to repurpose it during the times when you need it later. Some of the other things to be aware of, this is just a fantastic slide to showcase to you all the pain points other countries are experiencing. We have China in here, we have the French, we have Brazil, we have South Korea, we've got everything from Africa impacts all the way through Russia impacts. You can just go through and find all of these open source nuggets to say they're getting hit and we need the same supplies they do, which is causing prices to go up, as well as numerous other factors that are at play at this point. Some of the other things to be aware of, AI and data centers and their expansion, their need for energy. Our need for energy was going to go up anyway. The need for water to cool energy was going to go up anyway. AI coming to the forefront really suddenly surged that concern. The need for more data centers surged that concern. Where are we building these things? Are we planning for the floods, the droughts, the fires? Are we planning for water allocation rights? Are they on black water recycling systems? Are they making the most use of the water they currently have allocated to them? Or are they feeding off of the city's water, and the city is ill prepared for the amount of water that these systems need, but originally agreed to the contract because of the need for data centers and AI as we go forward? So this is just to be aware that ChatGPT 4 requires an incredible amount of water against GPT 3, despite being more efficient, because so many more use cases have emerged. So it is being used more. It's causing it to pull a lot more. And to be aware that in certain areas where it's developing, there are droughts, and it's going to continue to exacerbate a lot of those. So again, these slides are all going to be made available to you guys. You'll be able to see the impacts to other countries, things like China, Ireland, India, where their data centers have all taken hits from extreme heat and drought or from flooding. Things to keep in mind when you're building new infrastructure or allowing somebody to come into your infrastructure sector, to ask them if they've considered these impacts, because these are really good case points of what happens when you do not. So again, ending, this is the last nugget I'll leave you guys with before we switch over to questions. If you ever hear somebody say, well, why should we care? It was once hotter on the planet before, so this isn't anything new. they're not wrong. That's not an incorrect statement to say by the notion of what we have with our climatological data that goes back that far. It was once hotter. We weren't here. Our stuff wasn't here. My house wasn't here. I wasn't here. I have not acclimated to that heat. When it was that hot, creatures were larger. Alligators were more violent. Mosquitoes were massive. Disease was rampant for things that we've never been exposed to. We can't operate our current way of life in those temperatures. Nothing that we have built was built for those temperatures, for that extreme, for those severities, for the different problem sets that that'll bring with it. So if they ever say it was once hotter, remind them that everything that we rely on for our day in, day out has been in place over the last 150, maybe 200 years if you're talking about very old pipeline systems. But outside of that, we're not ready to be in that temperature, and it's happening too quickly to acclimate, and that's the problem set. So with that, that's everything. If you ever need to contact me, you can Google me and reach out through LinkedIn. I'm slowly working on making myself more available, as well as a lot of these repositories. So all that information will be available as we go forward. And I will hand over for Q&A now. Thank you.
Thanks so much, Sunny. Yeah, I think we can do 1 or 2 questions. So let's see what we had. How many years does the available data go back that is being referenced as a baseline or historical?
So we have various different data sets, everything from soil to tree rings to ice cores. So they can go back quite far. But if you're looking at for built infrastructure, I recommend, because most of the material types that we've chosen were established as a normalcy around 1850 to 1900, and then fully implemented from 1905 onward. So there's a big pivot that happened in 1905 to start adopting a lot of these. And then in the 1970s was when we had our third industrial revolution globally, where everyone started developing cities. So a lot of the cities, our metro systems, were put in the 60s to 70s. And then the 70s was this massive boom of commerce globally. So it really depends on which sector you're referencing. The water sector is one of our oldest as far as dams go. But a lot of the newer canals and the newer interconnectivity and the pipeline systems were not in place back, 200 years ago.
Got it. All right, let's do another one. Since California and other regions have used cloud seeding for precipitation enhancement and snowpack augmentation during drought conditions, are there any concerns about how this might influence regional storm behavior, water cycle stability, water quality issues, or long-term planning for hydrology and infrastructure?
100%. So I'm probably the largest advocate to quit with the cloud seeding. So we've been doing cloud seeding for more than 25 years. Some areas have been doing it for 40 plus years. When we're looking at where we've done cloud seeding, those areas were in drought when we started, and they're even more in drought now. So if we were saying this creates a 10% increase that we can trigger during a storm event for heavier rainfall, but we've never managed to get fully out of the drought, arguably not sustainable as a choice that we have funded millions and millions of dollars for every state. A lot of different states have been doing it. It's California, Wyoming, Arizona doesn't do it, but some of the other ones, Colorado does it, Mexico does it, China does it. China does it unabated. So if China has not figured out how much cloud seeding needs to be done to create a flash flood event on demand, some would argue it's not a viable option to continue to fund. I would also say that if we know that wildfire smoke inhibits rainfall, we know that the smoke creates more clouds but less rain because of how the water droplets interact with the pollutants. Some would say that it might be actually worsening the drought event because it might be changing the way that the water was going to operate. And it's very difficult once you cloud seeded to say that cloud was or was not going to rain and that you contributed to it in one way or another. Arguably, if we've been using it and we still haven't seen any viable path of making it rain when we need it to rain, I would say to pick a better thing to invest your money in, like fixing the pipelines in your area, covering the water system, changing the way your reservoir operates, where your injection points are for your aquifers. All of those things have immediate solves, immediate answers that they bring with it versus doing things like upper atmospheric modification in ways that we do not know how it benefits or harms upstream or downstream.
All right. Well, that is unfortunately all the time we have for questions today. For any questions we didn't get to, can do our best to get back to you offline via email. Just a reminder that at the conclusion of this webinar, you will receive an email with a link to download your certificate to use for Stormwater University credit or 1 personal development hour for attending the webinar. Thank you so much, Sunny, for taking the time today to share all of that important insight and information. And thank you all for attending. Our next session is a panel discussion titled Stormwater Management and Maintenance in a Changing Regulatory Landscape. You can join that session by exiting out of this one and going back into the agenda, selecting that session, and click on View. We will see you there. Thank you so much.